Hello, I'm Gustavo Neto and I'll present a work entitled Robust Point Cloud Registration based on Dense Point Matching and Probabilistic Modeling. This is a joint work with Manuel Oliveira from the Federal University of Rio Grande do Sul in Brazil. 3D point clouds are really popular and come as a direct output of 3D scanners and lidars. With the fast development of autonomous driving and 3D reconstruction, they are bound to gain even more importance. A fundamental task when working with them is aligning a pair or multiple clouds. This is called registration, and this image shows an example of such alignment in an outdoor scene where the red points are deformed to match the blue ones, producing the green point cloud. Notice that applications deal with static or deformable objects whose shapes can change during sampling. This is a different example where in addition to the cars moving separately, we have people whose limbs can move independently as well. This motivates the types of registration we'll cover in this work, rigid and unrigid. In the rigid case, the alignment consists of a rotation and a translation, and is typically represented by a transformation matrix. Here we have a challenge example where each cloud has noise over its points. In addition, they only partially match, one missing the upper part, the other missing their left limbs. Non-rigid, on the other side, can possibly have a different deformation per point. This leads to representing this registration by a vector field. In this example, the cat is complete, but some of its parts moved separately. The tail bent down, while the front legs went up. This is a more complex and challenging task compared to rigid. With the evolution of neural networks, the state of art in point cloud registration has been mostly achieved with deep learning. However, these works have focused more on rigid registration. They can target scenarios with noise and partial clouds. From them, we highlight DCP, which was the first to use an attention module on registration, RGM, which solely concentrates in estimating the correspondences between clouds, and Predator, which outputs deep features and rely on Hansak. This robustness does not appear on learning-based works for non-rigid registration. There are actually few approaches targeting this direction. FLOT focuses on scene flow using optimal transport modeling. RMA-NET is an unsupervised approach based on recurrent model. Neuromorph tackles mesh interpolation and registration in an unsupervised fashion. Still non-rigid, most of the literature is made of traditional approaches that are robust to noises, but have issues with larger deformations. Furthermore, they are typically based on expensive and complex optimization loops. From them, we have BCPZ, which models registration in a probabilistic fashion. We highlight 3 points of its formulation. First, it considers that target points have a probability of being outliers. If they are not outliers, they have a probability of matching a point from the source cloud. Finally, target points are sampled from Gaussian mixture models defined by the source points. To tackle the limitations on non-rigid registration, we propose a learning-based technique to register point clouds. It is robust to noise and can deal with partial clouds. In addition, it achieves state-of-art results on rigid registration. Our approach consists of two main parts. First is a neural network that produces a dense set of correspondences between points in the source and target clouds. Second, a probabilistic model uses the correspondence to estimate the final registration. Given the presented context, this work offers the following contributions: a robust learning-based technique for rigid and non-rigid registration, a neural network to estimate correspondences between 3D point clouds, and a self-supervised training strategy for non-rigid registration. We name our approach Robust Dense Registration, RDR, and differs depending on the registration type. On non-rigid, we have as mentioned two steps. First is the correspondence estimation by a proposed neural network. The second is a probabilistic refinement that through an iterative optimization computes the final registration. On rigid, we have the same neural network, but followed by estimating rigid transformation with SVD. This process also uses cyclic consistency and multiple iterations. Our proposal network adapts superglue to learn the correspondence matrix between clouds. The original superglue estimates correspondences of sparse key points in pairs of 2D images. The network has three main modules. The first module, feature embedding, learns deep features from each point based on its coordinates and its neighborhood. It has 5 layers, each building on the previous ones, so recursively accounting for more neighborhoods. Finally, we join all levels into a final feature, thus considering all 4 levels of details. The attention module enriches the features with information from any point in the same or opposite point cloud, self and cross respectively. To achieve this, each feature point is summed to a weighted contribution of all other features based on how similar they are to the compared one. In the thus being seen horn module, we estimate an initial correspondence matrix with the dot product of the enriched features. To account for partial correspondences, we refine their scores using the sinc-horn operator with extra assignment possibilities, called dustbins. This operator consists of alternatively normalizing rows and columns, while making sure dustbins can be matched by any number of points. This is the pseudocode of our probabilistic refinement, and we highlight sections of it. We take as input source and target, and the input parameters, and generate the deformed source cloud, called registration. We call the neural network for each outer iteration, and we pass the target and the current registration. We also use a nested inner loop, and this was adopted to avoid parameter instability during optimization, and special of the variance. After the correspondence estimation, we permutate the target cloud while considering how much we trust each correspondence. In the inner loop, we apply motion coherence, which infers deformation on points whose correspondences are not reliable based on their neighborhoods. This is followed by the registration using the SVD algorithm. Finally, we optimize over the variance, with the weighted average distance from the registration to the target. On rigid registration, we use the same neural network to estimate the correspondences. In addition, we loop between correspondence estimation and computing the optimal transformation with SVD. On each iteration, we convert the soft assignments to hard ones with the Hungarian algorithm. And after the iterations, we use cyclic consistency to estimate the final registration. Our loss function expands the cross-entropy adopted by RGM by including a new term. This is inspired by loss functions proposed by CineFlow and rigid registration approaches. The new term evaluates if a source point has any match in the target, and the main objective is to reduce false positive correspondences. Even though this is indirectly covered by comparing all correspondence matrix, this proved itself beneficial. False positives can deform a whole neighborhood given the motion coherence concept, which can damage the entire registration. A problem with non-rigid registration is creating datasets, since it's necessary to have different kinds of deformation and point-to-point correspondences. Rigid registration works deal with datasets by simply randomly creating rotations, translations, or even partial clouds. We follow this path for the non-rigid case, by using the method proposed by Hirose to generate synthetic deformations. It consists of applying a guided noise while keeping the overall shape. The noise comes from the eigendecomposition of the source cloud correlation matrix, the same used to enforce motion coherence on BCPD. First, we report results on non-rigid registration. We experiment with 4 different scenarios: clean, cropped, holes, and outliers. We compare against 5 techniques that solve this problem or adapted by us to do it. The adaptation consisted on using the correspondence produced by Neuromorph and RGM with our proposed refinement. These are results comparing the mentioned techniques to ours, with and without the self-supervised learning on cropped clouds. In this scenario, we remove 30% of the points in a contiguous region. In addition, we classify impossible points in source without any matches in target, and color them magenta. Our Neuro and our RGM refer to our probability refinement used with their respective networks. We highlight how ours and our RGM have the best results. However, They have minor problems, like classifying the points around the hands or inferring registration in the legs. RMANet and BCPD deal well with the upper body, but struggle with the legs. These are results with the previously described setup on clouds with holes. In this scenario, remove 25% of the points in the target cloud, creating random holes around seeds. In these examples, we highlight how ours and ours Nero have the best results. However, they have minor problems, like correctly aligning the back legs. ArrowMayNet and Float cannot register the clouds. While the first gets completely lost, the second keeps the overall initial shape. In this scenario, 20% of the target points consist of outliers, random uniformly distributed points. We highlight how ours and RGM have the best results here. Float and RMANet cannot register the clouds. While the first keeps the overall initial shape, the second gets completely lost. Neuromorph cannot deal with outliers as well, while BCPD almost succeeds but misses the phi. We used two datasets for training and testing. The first was proposed by RMANet. The second was compiled by us and was inspired by the first dataset. We added randomly deformed objects and rigid transformations. We named it custom. The main metric used is the end-to-end point error, which computes the mean Euclidean distance between the deformed points and their correspondences. For experiments with partial clouds, we classify regions in the source cloud without match in target. We report precision recall for this classification. Overall, our method has the best performance in both datasets. On clean, our probabilistic refinement improves the results in up to 40%, with all the remaining scenarios using it. With outliers, ours can be 25% better than any other compared work. With holes, ours can be 12% superior to the second best and 30% better than the remaining. In cropped, ours surpassed the second in 45% with superior precision and recall. The exception is on clean, where Neuromorph was the best. For the experiments with rigid registration, we have three scenarios: clean, jitter, and crop jitter. We compare against state-of-art techniques all trained on the ModelNet dataset with crop noise. We adopted the metrics already employed by related techniques. The isotropic error takes the angular difference for rotation and Euclidean distance for translation. The anisotropic error does the average difference of the Euler angles and coordinates. This is an example comparing the mentioned techniques to ours in partial clouds with Gaussian noise. We highlight how ours have the best results. All the others misalign the stem in various degrees, with RGM being the worst. This example again compares the mentioned techniques with partial clouds with Gaussian noise. In the target, all the branch is missing and there is only the tip of a leaf to add context. Ours and Predator perform the best, while the other two incorrectly align the branch to the leaf. We start with the chart showing the evolution of the rotation errors for the two metrics. From left to right, it progressively gets more challenging as the final case crops 40% of the clouds. Overall, they show how our technique offers the best results, besides it degrading the least in more extreme cases. The main limitation of our technique is dealing with large deformations. This is an example where we mostly register the cloud, but some details are missed, especially around the hands and the right knee. The other limitation is generalizing to different datasets and keeping performance in both. This can be done by fine-tuning, but might be challenging. In summary, we presented an approach for 3D point cloud registration that combines the advantages of deep learning with probabilistic modeling. It achieves state-of-art results in both rigid and non-rigid registrations. On non-rigid, it is the first on our understanding that can learn deformations while being robust to noisy point clouds. For feature work, we believe it's possible to better integrate refinement and the network by informing the model with more than point clouds. This can be a first step towards the network learning motion coherence. We would like to thank our sponsors.